This is a revision video for P4E, Radioactivity, Radioactive Decay and Half-Life. Everything around us is made up of atoms. There are billions and billions of them in a tiny drop of water. Each atom has a tiny central nucleus with electrons in orbit around it. The nucleus of every atom contains protons and neutrons. There are lots of different types of atoms. The different types of atoms can be found as elements on the periodic table. When we look on the periodic table, we see that each element has a symbol, and it's also accompanied by two numbers. This one, which is the atomic mass number, which is the number of protons plus the number of neutrons in the nucleus, and then this one is the atomic number, or the proton number, which gives us the number of protons in that atom. If you want to know the number of neutrons in an atom, then what you have to do is the atomic mass number, take away the proton number, and what is left over will be your number of neutrons. In this case, we're doing 7 minus 3, which gives us 4 neutrons. Here are two examples for you to have a go at. We have uranium, which has a mass number of 235 and a proton number of 92. And then we have got thorium, which has got a mass number of 228 and a proton number of 90. So if you stop the video now, then you can work out the number of protons and the number of neutrons in each of those atoms. Thankfully, the nuclei found in most atoms are perfectly stable. However, the nucleus in a small number of atoms is unstable, and radioactive decay occurs when this nucleus breaks down and emits one of the 3 types of ionizing radiation. The number of radioactive decays per second is called the activity. A radioactive substance might have an activity of 20,000 decays per second. Inside this substance, the nucleus of 20,000 atoms breaks down every second. Okay, so now we're going to talk about the 3 types of ionizing radiation. The first type of radiation we're going to discuss are alpha particles. They are given the symbol alpha. They have a mass number of 4 and a proton number of 2. They have got the same nucleus as a helium atom. There are no electrons around the alpha particle, so it's just the nucleus. So the particle is made up of 2 protons and 2 neutrons. So out of the 3 types of ionizing radiation, this one has got a relatively large mass. It's also got a large positive charge because it's got 2 protons, and that means there are 2 positives. If you remember, neutrons are neutral, so they don't add to the charge at all. And then because of that charge, this type of radiation is the most ionizing type. The second type of ionizing radiation is the beta particles. They are given the symbol beta. They have a mass number 0, because they're not made of any protons or neutrons, and they have a proton number of -1, which becomes important when we start talking about the decay equations. Beta particle is a fast-moving electron. It's got less mass than an alpha particle, because it's only made up from that one electron. And because electrons have got a negative charge, then the beta particle has got a -1 charge. So although it is ionizing, it's not as ionizing as the alpha particles because its charge is only -1, whereas the alpha particles got a charge of +2. And the last type of ionizing radiation is gamma radiation. It's given the symbol gamma there. Its mass number is 0 and its proton number is 0. It's a high frequency electromagnetic wave. You might remember it from the electromagnetic spectrum. It's got no mass, it's got no charge. It's not very ionizing as it doesn't have a charge, and it can travel a very long way. It's very penetrating. Alpha particles, beta particles and gamma rays are all described as ionizing radiations. They ionize the atoms of any material they pass through. Atoms are usually neutral. They have no overall charge, as the positive charge from the protons is exactly cancelled out by the negative charge from the electrons. When an atom gains or loses an electron, it becomes charged, as the charges are no longer balanced. An atom charged in this way is called an ion. When ionising radiation passes through a spark chamber, it ionises the gas inside by removing some electrons from the atoms. This causes an electric current, which is seen as a spark between the metal plates. Both alpha and beta particles have charge. When they pass close to atoms, they either attract or repel electrons away from an atom, ionising them. Alpha particles have a greater mass and a greater charge. This makes them the most ionising form of radiation. How far radiation can travel depends on how ionising it is. The more ionising it is, the more quickly it can slow down and is stopped. Alpha radiation can travel a few centimetres in air and is stopped by paper. Beta radiation can travel a few metres in air and is stopped by an aluminium plate. And gamma radiation can travel several kilometres in air and needs metres of concrete to reduce it, and even that doesn't stop it altogether. A substance that contains radioactive atoms gives out radiation all of the time. The nuclei within it decay. As you know, the number of these decays per second is called the activity. In a radioactive substance, atoms are decaying all of the time. As time passes, the activity gradually decreases. An example can be seen in the table below. At time 0, the activity is 2000, and then if we go to 60 years, the activity is decreased to 370. As the radioactive atoms within a substance decay, fewer and fewer radioactive nuclei remain. This leads to a drop in the activity as time passes. The time taken for half of the radioactive nuclei in a sample to decay is called the half-life. This is the time it takes for the activity to halve. The average time taken for half of the radioactive nuclei in a sample to decay is called the half-life. It's the same time it takes for the activity to halve. If you plot a graph of the number of radioactive atoms remaining, or the activity, against time, then you can use it to find the half-life of a substance. After one half-life, the number of radioactive atoms remaining, or the activity, will have halved. So on our graph, we've got starting activity of 2000. If we want to find out the half-life, then we halve that activity to 1000. We can draw a line across to where it meets the curve and down. And that comes out at about 18 years for the half-life of this isotope. If we were to halve the activity again to 500, draw a line across to where it meets the curve and down, you should see that it's taken it another 18 years to reduce by half again. We can also reduce that by half again, so go from 500 to 250, draw your line across, and then down it reaches the curve. We should see that it should have taken another 18 years to halve again. So in this example, 3 half-lives is a total of 54 years. Different substances have different half-lives. These range from milliseconds to billions of years. The table shows a few examples. Nitrogen-17, for example, has got a half-life of 4 seconds. If we go to uranium-238, this has got a half-life of 4.5 billion years. These isotopes have got different uses depending on their half-life. Some of them are used for dating very old objects, some are used for tracing leaks in pipes, and some are used for medical applications. Okay, so that brings us to the end of this section on radioactivity, radioactive decay and half-life. You can stop the video now and have a work through these graded questions.